Uh, the first time is a special lecture one, value-based electricity resource planning in modern era. Will be given by Professor Rajesh Karki. He's a professor at University of Saskatchewan, Canada. Okay, Karki,
Yes, Professor Choi.
thank you so much. Please, yeah, okay, you can.
Yes. Well, thank you, Professor Choi, for inviting me to participate in this workshop, and also for the opportunity to have this MOU with my university to work in collaboration in this research against disasters and natural disasters, uh, and and to you know plan and design uh, resilient electric power systems. But today I will slightly touch on value-based electricity resource planning in the modern era. Now, when I say modern era, I would also like to um, slightly discuss the changes that are happening in today's electricity systems because of the concern with environment. So that means more renewables coming into the electricity system, and also the concern. I will also slightly touch on concerns with natural disasters and how that might affect this value-based planning from that context. But the bulk of my lecture today is on value-based reliability planning, and I will refer my recent work that was done for Saskatchewan Power Corporation. We did a project for value-based reliability planning for their electric systems. So I will base my lecture on the work that we did for them about 3 years ago. Uh, I'm again, this is just to give you a little introduction of my university and my research group. I'm from the Power Systems Research Group. This research group has a long history of research excellence, especially in the area of power system reliability. And that was established many, many years ago under the leadership of Professor Roy Billington. And there are many graduates that worked with Professor Roy Billington, and I'm one of his students uh, from the group. So there have been many IEEE fellows from this power system research group, and many internationally known researchers in the area of power system reliability, such as even Professor Choi has been part of this power systems research group in the past, and still there are collaborations that is happening right now. So just a little background of my research group. And we are from the University of Saskatchewan. And just to give you an idea where that is in Canada, so I have this map of Canada. Let me see if I can use a button here. Okay, the map of Canada here that shows the different provinces. And here, right here, is the Saskatchewan province. And this red star that you see on the map, that is where the University of Saskatchewan is located, in a city called Saskatoon. I'm losing the mouse here. Okay, right here. And we did this value-based reliability evaluation project for this province of Saskatchewan. which has a population about 1.1 million. Canada has total about 37.6 million. The total installed capacity, electricity generation capacity in Canada is about 146 gigawatt. The Saskatchewan province electricity demand is only about 4% of the total Canada demand. And just to give you an idea of the electricity generation resources in Saskatchewan, I have on the right, I have this map of Saskatchewan. Let me try to find a, okay. Okay. Mouse, there it is. Okay, so here, this is the province of Saskatchewan, and the different electricity generation resources are shown with different colors. Basically, the coal used to be the main source of energy from many years back, but because of these environmental concerns, that is gradually being replaced by natural gas. So today, the major source of energy comes from natural gas. Since the last 10, 15 years, there has been a rapid growth in natural gas. And after 2030, all the coal is going to be removed from generation resource. We have some hydro, and there is also growing integration of wind power. So right now we have about 241 megawatts of wind. So the electricity scenario, the supply scenario is changing because of these environmental concerns. And obviously now that creates investment issues in order to find what's the right level of investment in the right type of energy resources in order to be able to provide the customer with reliable power supply for their day-to-day energy needs. Now is the paging. Slide is paging. I'm having a problem with my slide. I'm trying to. Okay. So here I just want to show you the electricity demand profile and annual profile in the province of Saskatchewan in Canada. So on the left, I have this energy profile for the year 2009. And you can see, looking at this profile, Saskatchewan is mainly a winter peaking demand. In the summer, the demand is very low, but the peak demand occurs here in the winter time in December. In 2009, the peak load was 3,156. But in the year 2015, we did this project in 2016. So we were looking at this demand in year 2015. So you can see the demand has increased, and also slightly the shape has changed. You can see in the summer you're getting more air conditioning loads coming up, and the peak load, but it still is in the winter time. So the peak load now increased from 2009 to 2015. It increased to 3,682 megawatts. The following year, in 2016, that further increased to 3,710 megawatts. So we see a gradual increase in demand for electricity. And this is obvious, the increase in demand with time due to population growth, industrial growth and other economic development going on. But more interestingly, as we look into the future, there's going to be a significant growth in demand, because even our transportation needs that are currently in gasoline will eventually be, fueled by electricity. So that will lead to substantial growth in demand. So as this demand increases, there's also more reliance on electricity by the society. The society is depending more and more on the electricity system, and they are relying. So any disruption in electricity is really going to be a greater problem as we move into the future. So therefore, there has to be new investment in the generation resources as well as in the network facilities in order to maintain an acceptable level of reliability. Now, any investment that is made in the electricity system will eventually be recovered from the customers. So even though the utility makes the investment or third party makes the investment into the system in order to maintain the reliability of the customers, that investment cost will be eventually borne by the customers in terms of electricity price. So the more investment they are going to make, the customers are going to pay more in terms of electricity price. So therefore, what is the right level of investment? Excessive investment means the customers are paying too much price for the electricity. But it also depends on not only on how much to invest, but in what resources to invest, because there are different options. In the past, most of the generation resources had firm capacity. We call them conventional resources. For example, thermal generation, nuclear generation, hydro generation, and so on. But this environmental issues has really given a lot of support to investing in renewables. And with renewables, obviously, there are a lot of problems. The investment that we make in renewables, how much is that really helping to maintain the reliability? So these questions need to be answered. And also, there is a big interest nowadays to invest in energy storage in order to mitigate this variability with intermittent renewable resources. And these are, again, in terms of investment, do the investment in these resources, are they worth the investment to the customers? So that's a key question here. So investing in different types of resources and in different types of technologies obviously is going to have different impacts on the cost of investment, and therefore that is going to be reflected in the electricity price which the customers are going to pay. For example, I have this data from electricity price in Canada for the year 2015. The most of the data I'm showing you is from the year 2015 because we did this project in 2016, so these were the latest data at that time. So if you look at the electricity price in the different provinces in Canada, so this is the British Columbia province, this is Alberta province, this is Saskatchewan province, this is the province from where we are. And this is the electricity price in cents per kilowatt hour for the residential customers. You can see the price is different for the different provinces, and that is mainly driven by the resources that have been invested in. Now, obviously, the generation resources make the biggest impact on electricity price, mostly about 90% of the effect, 90% of any investment is in the generation facilities. So they have a big dominant impact on the electricity price. So if you note here, the lowest price was for Quebec, province of Quebec. And then if you look at the resources, electricity generation resources in Quebec, it is 91% hydro. And we all know hydro power is one of the cheapest technology, and that can provide very reliable supply because they can provide very firm power and very quick ramping capabilities. And similarly, this is the most expensive electricity price was for the province of Prince Edward Island. And in Prince Edward Island, this is a smaller province. So if you look at the resources there, they heavily invested in wind. So bulk of their generation comes from wind power, and then that is being balanced by diesel fuel, which is also very expensive, which is a very expensive resource. So because of that, now all this investment being reflected in the electricity price, so you can see that's why they are the most expensive. So again, going back to this, so the investment that is made for maintaining reliability eventually is going to be reflected in the electricity price. And that investment, when they make the investment, that should work to maintain the reliability. So in value-based reliability planning, we want to evaluate, is that investment really helping to maintain reliability, or how much is it helping to maintain that reliability? Okay, because if you don't make sufficient investment or inadequate investment to maintain reliability, is going to cause excessive power outages. The power outages are going to increase. And so when you have increased power outages, now that is going to increase the outage cost to the customers. So again, if you invest too much, the customers will be paying a higher electricity price. But if you invest too little, there is going to be excessive power outages, and therefore that's going to increase the outage cost to the customers. Now, these monetary losses incurred by the outage of electricity supply to the customers, we call that the customer interruption cost. So this term customer interruption cost, I will be repeating quite often in this lecture. Now this cost, because of power interruption, that can be divided into direct cost or indirect cost. Direct costs are the cost that is directly related to that power outage. And you can have economic costs or social costs. Economic costs are easy to calculate. These are like loss of production, product spoilage. If it's industry or commercial customer, then there will be staff that are not working, but they are still paid. So these are direct costs that can be easily calculated. But there are also social costs, such as risk or injury because of power outage, lack of transportation, and especially in Canada, we have the situation where power outage in the wintertime is causing a whole entire community to have no heat, and the temperature at that time is very low. It could be minus 40, minus 50 degrees. So that that has a big impact on the society. So it's a challenge to to translate these into societal costs. But these are costs outage related to the outage of the power. And again, there are indirect costs as well. For example, you see the cost of changing the way you do business, changing the schedules and having to invest in backup supply and so on. So all these costs, they add up to quite a significant amount when you have power outages, especially to different, there are different types of customers, residential customers, industrial customers, commercial customers. So the same power outage will have different amount of outage cost to the different types of customers. Now, this value-based reliability investment planning is really to see whether the cost to the society of providing a certain level of reliability of electric supply is justified by the worth or benefit that is provided to the society of having made that investment. So if you look at this diagram that I have here, so I have these different colors. The blue color shows the utility investment cost for reliability. So on this y-axis here, I have a dollars. So if you want to increase the level of reliability, the utility, you will have to increase the investment. So, and it is shown by this blue, line over here. So as you see that if a system has a relatively poor reliability, even a small investment can make a big improvement in reliability. But as the incremental reliability decreases, okay. But as the system becomes more reliable, there will be less outages, and therefore the outage cost will decrease, as shown by this red line here. So this is the interruption cost, or the cost to the customer due to lack of reliability. Since both these costs, investment cost and the outage cost, are both borne by the customers, they are both seen by the customers, they are both have to be dealt by the customers. If you add them, that is the total cost on the society, or that is the total cost on all the customers in any society. So we call that the societal cost. So the sum of the two is shown by the green line here. So that is the total societal cost, and obviously the target would be to minimize that societal cost. So at the minimum societal cost, whatever level of reliability is associated with that, that is the optimum reliability that is desired by that particular society. So in value-based reliability planning, we want to make sure that we make an investment so that the societal cost is minimum. So in order to do this, we need to be able to plot this figure. So we need to be able to calculate what is the investment cost for any investment plan that the utility has. And then based on that investment, what is the interruption cost to the customers? Now this investment cost is easy to calculate. If you ask the utility people, they will be able to give you a figure of what any investment option is going to cost. But the customer interruption cost is not that easy to calculate. And there are different methods to calculate the interruption cost. Now, in general, the evaluation methods can be analytical approach. And so analytical approach basically, they deal with electricity rates because they are related somehow to the outage cost, especially in a market economy. And also the gross economic indices, the more the more industrialized the country becomes, the more reliance on the electricity system. Therefore, there will be higher cost of outage. And so these methods actually then use this kind of approaches to estimate the interruption cost. Now, another method is the impact studies. That means after a recent outage has occurred or a blackout has occurred, then going back to the statistics of outage that has been as a result of these blackouts, and try to figure out what was the cost of that particular outages. Now, these impact studies is more like a after event study, and then trying to figure out what was the cost of outages. Now, the third method in this slide that I've shown is the most widely used method or most favored method by most utilities, which is using a customer survey. So this involves developing a questionnaire. Obviously, there are different categories of customers, so these questionnaires has to be different for different categories of customers, and they have to have the right questions in order to extract the data that you really need to be able to calculate this interruption cost. And obviously, this was the approach that we had used when we did our project 3 years ago. And if you go back into the literature, there have been several customer surveys that have been done in the past as well. Okay. Now, the techniques actually to calculate the interruption cost, there are different techniques out there. In certain cases, you can directly calculate the losses. For example, this is in the case of economic losses that can be directly calculated. Now, in certain cases, you cannot directly calculate them, so you need some other approaches. And some of the approaches are willingness to pay, willingness to accept. That means asking the customers, are you willing to pay more for reduced outages, or are you okay with the level of outages that you're seeing, or would you be okay to even have more outages but you're paying less electricity price? So these are certain methods, okay, and there are other indirect estimation methods. For example, if these outages were to increase, how much would you spend in the backup systems or other preparatory actions, or what kind of compensation would be justifiable to you for lack of for customer interruptions and so on. So in our questionnaire, we involved all of these three techniques to obtain this interruption cost for the province of Saskatchewan. Now, once you prepare this questionnaire, what must be also realized that the cost to the customer will also depend on the duration of the outages, long outages versus short outages, and also frequency of the outages. If the outages occur frequently, what are going to be the cost versus if the outages only happen once in a while. So these are both sensitive to the outage costs of customers. And the outage cost will also depend on the time of day, on whether it's a weekday or a weekend, or is it in the winter time, or is it in the summertime, and so on. So all these things have to be part of evaluating the customer outage costs. And also, you need to know what would be the worst case scenarios, and so that puts an upper limit to these outage costs. Now, in this approach, after obtaining this data to calculate the outage cost, this must be somehow embedded into a interruption cost parameter. And the parameter that is widely used is called the customer damage function. So this customer damage function is actually a variation of interruption cost with outage duration. Now, if you look at on the bottom right figure here, so on the y-axis, I have this interruption cost, which is normalized by the demand, dollar per kilowatt. And on the x-axis is the interruption duration in minutes. So in general, you see the longer those durations of outages, the cost per kilowatt increases. But that is different. You can see it is different for different types of customers. Now in Saskatchewan, the Saskatchewan Power Corporation, they categorized their customers in terms of industrial, residential, commercial, oil fields, and farms. And there were a few other categories too, but they were, you know, the percent share of them was very, very little, so we neglected them. And you can see the, you know, the different customers category, their share in terms of demand, and in terms of energy consumption. So obviously, once we get this cost of outage for each of these different types of customers, we average them for that particular type of customer. We call that sector, residential sector, in the oil, industry sector, and so on for each sector, because even within each sector there will be further classification. For example, in residential, you will have people in the rural areas versus people in the urban areas, and people living in individual house versus people living in high-rise towers. So we need to do the sampling in the proper way, and then proper weighting, and to average them to find what is the interruption cost for one particular sector. And then we normalize that by the demand or by the consumption. In this case, you see this is dollar per kilowatt, which is normalized by the demand. And then you can then combine the different customer damage functions for all the different sectors into a composite customer damage function. We call that composite customer damage function, CCDF, which is the dollars per kilowatt of customer outage for different interruption durations for the entire combined, for all the customers combined together. So in this figure, in the right bottom, the dashed line, the line with dash, and that combines all the different types of customers into a composite customer damage function. And then this can be used to calculate the expected interruption cost in the reliability worth assessment. Now, so the reliability worth assessment is to find what is the expected interruption cost looking into the future. Like if I do a certain upgrade into the system, if I invest in a certain upgrade, this is I can calculate my investment cost. But then what will be the expected interruption cost? So that is what we call the reliability worth assessment. Now, in order to do this, we need to do a reliability evaluation, but with the capability of frequency and duration techniques, because we need to be able to find the frequency index, the duration index as well. And two broad methods to do this worth assessment using this reliability evaluation is an analytical method, using contingency enumeration or a simulation method using the Monte Carlo simulation. Now this contingency enumeration, so in this method, each outage contingency is enumerated to see whether that causes a power outage. And then what is the frequency of that contingency, and if that contingency leads to a power outage, how long are these power outages, the duration of these power outages. Okay, so F is the frequency in this equation of that interruption, how often it happens for a given contingency. And then D is the duration. And then from this duration, we go back here, and for that duration, we find what is the interruption cost per kilowatt, and then multiply that by the average load that is curtailed by that particular contingency in order to get the cost. And that is then aggregated for all the contingencies to get the expected interruption cost. Now, in this, we can use the composite customer damage function if we're doing it just for the entire, we call HL1 study, for generation reliability study. Or if we are doing this for transmission lines or distribution lines, then at each load point, you are going to have a different combination of the different customers. So therefore, we need this customer damage function for each of the customer sector, and then for each load point, we have to find what is the composite customer damage function for that particular load point, and then use that in this particular equation to get the expected interruption cost. Now, the Monte Carlo simulation approach, you simulate the system in hourly intervals, and then find when you're going to encounter an outage, and when that outage does occur, how long that outage is going to last. And based on the duration, you go back to this customer damage function and find what is the dollars per kilowatt of outage, and then using this equation here, you calculate the expected interruption cost. Now, there are also approximate methods where you don't need this frequency and duration indices, and you can, using just the expected energy not supplied for the system, and using this index called average interrupted energy assessment rate. In order to find this, you have to do a frequency duration technique in the first place, but then you assume that this remains constant, and then you can use this index for different planning options or investment options. Now, this value-based reliability planning, in our project with Saskatchewan Power Corporation, our project was mainly investment in generation capacity. So we were only looking at power outages that is caused due to lack of generation supply. And the lack of generation supply mainly is important during the peak hours, of the year when the demand is the highest. That is where you're going to get lack of supply. So most utilities, what they do is, if this is the peak load, they need to invest in generation facilities to not only meet the peak load, but also have a capacity reserve. Now, that capacity reserve above the peak load is required to maintain the level of reliability. Now, in this case, just a second here. So, in this case, you can see, and as an example, this shows a capacity reserve of 12.5%. Now, that may be, you know, appropriate, or that may not be appropriate. Now, NERC, North American Electric Reliability Corporation, they suggest a planning criterion using a probabilistic index called loss of load expectation of 0.1 days per year. Now, in our project, we wanted to find if this criterion was suitable for Saskatchewan. Now, different uh, utilities have different combinations of resources, so they are very different in terms of the investment that they make, and in terms of the value of the investment that they make, because they are totally different resources. We have some totally hydro dominant systems, some systems that have a lot of thermals. So obviously this 0.1 days per year may not be suitable for all utilities. So that's why this project was looking into this. So, but when the question is just for generation capacity, then the question becomes then what resources, how is renewables, investment in renewables going to provide worth to reliability? For example, if you look at solar, the solar will have very little impact in terms of reliability worth from a generation capacity, because the peak load occurs in the winter time in the evening, and then you need so much capacity plus reserve to maintain reliability, but you are not going to get any sunshine at that time. So therefore solar will have very little impact or very little value for the investment that you make for generation capacity to maintain acceptable reliability. So but then if you have energy storage, then you can store that energy, and that can be again used at that time to give a value to solar. So these are the types of studies that really need to be looked at from a generation capacity reliability planning. And then based on the different investment options that are available, what are going to be those investment costs, and what are going to be the outage costs from the reliability evaluation, and putting those two together to find the societal cost and the minimum point of that societal cost. So is that 0.1 days per year, or is that different? So we actually, in our project, we came up with something very close to 0.1 days per year for our system. And obviously our system is in Saskatchewan is a very typical conventional system with thermal, mostly thermal dominant with some hydro. So therefore, the 0.1 days per year was more or less close to what we got for the optimum reliability in our case. Now this value-based reliability planning, this approach can also be used for the bulk system for transmission planning, as shown by this example here. Now, one thing that has to be, you have to be careful applying this to transmission. Now you can get power outages not only due to lack of supply, but you can also get outages due to the failure of the transmission lines. So therefore, we're not only interested in outages during the peak loads, we are also interested in outages that can happen at other times. So therefore, this composite, actually this, in this particular study, we use the same composite customer damage function, dollars per kilowatt, that was used for the generation capacity planning. But actually, this has to be slightly different, because for generation planning, when you do dollars per kilowatt, you're normalizing that by the peak demand, because we're really looking at investing to meet the peak demand. But when doing this for bulk transmission planning, this can happen at any time of the day. So then this normalizing kilowatt demand has to be the average demand of the system. So when you do that, these values dollar per kilowatt tend to increase. But the approach is again using the reliability evaluation to find for each of these load points, to find the frequency index, the duration index, and then based on that duration index, find what is going to be dollar per kilowatt for that duration outage, and then calculate the E cost, the expected interruption cost. And the next step is combining this E cost. So in this case, in this example, there are 4 investment options, because this is the Roy-Billington test system, and without these dashed lines are upgrades, and without these upgrades, this Roy-Billington test system, you can see has this in the different bus, these are the values of the E cost. So this is the total interruption cost, which is $548,000 per year. So now, investing in transmission lines, you can lower that interruption cost. Sorry. And these are like comparing these 4 different investment options. You know, this investment in transmission line A, option A, B, C, and D, and calculating what is going to be the E cost for that 4 different options showing on this table over here. And the next step is then to calculate what is going to be the investment cost of those 4 options, and then find which gives the minimum societal cost. That would be the preferred investment plan. And this is another example of value-based reliability planning used for deciding investment in wind integration. Now, this work was done by Professor Billington and one of our PhD student, Vijan Wangdi, and this is also published in the IEEE paper here. So where this shows, this is an IEEE RTS system right here, and in this IEEE RTS system, if there is going to be a wind site close to this bus, that wind owner will want to connect to the closest point to minimize their cost. So let's say now this part is blown over here. Let's say there is 240 megawatt of wind at 2 close locations that has a certain cross correlation between the 2 sites. And then using double transmission lines, it is then connected to bus 1. Now the bulk system planner, or this could be a system operator in a market structure, will then need to figure out, in order to absorb this 480 megawatts of wind, which is connected at this bus, by that entire system, and then get the maximum worth in terms of lowering the outage cost. Different transmission upgrade options can be analyzed. So here you can see 5 different options are considered, just to show as an example. And for each of these options, we can calculate what is the annual capital payment in terms of investment, and then do the reliability study and find what is the e-cost, and then figure out which option gives the minimum societal cost, and that would be the option to take. Now, in the end, I just want to slightly relate this to resilience, value-based resilience investment. Now, this is something that is still in process. We have just kind of started working in this resiliency area. Now, here the difference is that we are dealing with high impact, low probability events or very extreme events. Now, these are mainly natural disasters. We are in North America. We are mainly concerned with natural storms, high extreme wind events, and in other parts of the world, I think earthquakes and other natural disasters that could. Well, this pandemic, I think that could have big impacts in maybe other areas, but maybe relatively less impact to the electric system, the way that it is functioning. Now with smart grids and depending more on the cyber side to automation and control the physical side of electric networks, now there are also threats of malicious attacks that can have extreme impact on the system. So as a result of this, it also becomes important to then really assess whether investment should be made into the system to make the system more resilient, and then what is the value of that investment to the customers, because eventually the customers are going to pay for all of these things. Now, resilience investment could be made in infrastructure hardening, for example, in stronger towers or replacing overhead lines with underground cables, and increasing investment in cyber security and so on. And it could be investment to increase the flexibility of the systems, to have more flexible resources that can withstand these extreme events. Different types of distributed energy resources, distributed generation, energy storage, having capability of islanding so that even when these disasters happen, certain parts of the system will be functioning on an islanding mode and so on. And obviously increasing connectivity, data access, communication, automation, and so on, so that you can rapidly recover from these extreme events. Now, the damage cost, now it becomes important to assess the damage cost due to these extreme events. And the damage costs in this case could be not only the outage costs, but also the restoration cost, because you could lose a power plant, or you could lose all the wind turbines in an area. So there's again this restoration cost, which is going to be a really significant cost in terms of extreme events. And I talked about these failure impact studies. Now, Professor Choi mentioned that obviously there's lack of data. Now, in reliability study, we do have a lot of data collected over time, but in these extreme event cases, these are very rare events with no data. And these failure impact studies, I think, are going to be very important in order to assess these damage costs. And also, among the affected customers, I think also important that there are some critical customers, or there are some critical load points. Now, it may not be feasible or justifiable to invest to make the system resilient so that all the customers are always, always served. So I think it becomes more important, because that's going to be a lot of investment, and that's going to be very costly. So it becomes important to have critical load points. Know that these critical load points are 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 maintained, or the system is has sufficient resilience to have the necessary uh, uh, functions operating during these extreme events. So so therefore, this, the development of customer damage function is going to be quite different than in the way that we do for reliability. And so the total social cost, eventually we need to minimize the societal cost, whether it's reliability studies or for resiliency studies. So the societal cost of extreme events, now they, in addition to the damage cost, there's going to be investment costs. There are also added utility costs which are not known uh, in general reliability studies, and so these are the things that need to be really looked under this research. And in reliability studies, all of our indices are per year, but here these are events that are very, very low frequency, and this may occur once in, say, 20 years, 30 years. So any investment we do in any resources, that resources may not have the life span to encounter that extreme event. So these things are to be considered in this study. And then obviously, in any resiliency study, this comes from one of our IEEE paper, is the steps that we followed is that we need to model the extreme event, its likelihood, and using probabilistic techniques, and then also the kind of damage that it can cause, the damage assessment model, and the optimal restoration model. So with this with this, then we can estimate what would be the indices, the resilience indices that need to be used in resiliency study to obtain this overall societal cost and to minimize that societal cost, to see whether that investment is justified by the worth. In conclusion, I see that I've exceeded my time, so I'm in the last slide. I kind of rushing over things. Anyway, in conclusion, the demand for electricity continuously increasing. So therefore, investment needs to be continuously increased to maintain reliability. But then, is that investment really providing the worth to the customers? Is that needs to be assessed. So a value-based reliability assessment must be then applied to justify the investment in the different resources, in transmission lines or other major components, in smart technologies, and so on, so that that those investments are justified. And in terms of resiliency, again, this approach needs to be somehow extended, so that we can decide whether any investment we make to make resilient systems is actually providing the worth to the customers. So with this, I'm sorry to slightly exceed my time, but thank you again for your attention, and I would like to stop right here.
Okay. Thank you so much, Prof. Karki. Yes, thank you very much. Okay. Please, 1 second. One question. Yeah. Can I? Okay. Please, okay. Question. Just only one. Okay. Karki, I understand very well. I am focused on in the interest in this area. And as you know, this IEEE Power Energy Society maybe they will open the Montreal, Canada maybe.
Mm.
But is the cyber workshop conference was delayed on the so as you know this is the some difference between the resilience reliability but is that difference is some the area this resilience is focused on the reliability area my opinion and so uh, just only this different is for how much the frequency the extent frequency is yeah,
Mm.
different yeah but it's the so please the e cost I am the thinking about is the please sliders e cost the IR close times the ENS sliders yes okay my opinion as you know this is HOMER Homer is for microgrid the simulation program is made by the FRE is
Mhm.
some very nice and so my student is the starting the by using the Homer and the but is the some Homer is the calculation is the construction utility cost is the some focus on the but is the some Homer is the cannot simulate some renewable energy generators considered some conventional generators and so I am now is in recently is the some similar home similar the toolbox is the made I hope my opinion and so IAR is the so another the two category IAR is the outage cost assessment we have in order to implement the E cost two categorized. We have the two. One is the IAR calculation.
Mhm.
Another is the ENS
Mm.
calculator. Yeah, IAR is the not easier. Is the so as you know as
Yes.
you mentioned. Yeah, IAR is the survey and the macro and the micro methodologies. But it's ENS also in now is the as you know this is the consideration of the renewable energy generators as well as the ENS ESS energy storage system is the so how is the simulation the considering renewable energy generators how is the simulated in order to calculate the ENS is some not easy maybe the can you suggest some how is the tool EENS the consideration considering the renewable energy generators simulation some difficult as you know probabilistic simulation toolbox tool is the maybe the I hope the for near future take discussion is the some how is the toolbox tool is the some as like as the Homer HMER is the so uh, the renewable energy generator considered the generation probabilistic generation simulation. Okay, I hope to take a discussion. Okay,
Yeah.
for
No,
future.
I think you raise a very interesting
Yeah.
point. With renewable energy generation, there are a lot of
Yes.
uh, challenges, of course.
Yes.
Uh, Now, this calculation of E and S,
Mm.
in this equation, this is a very general equation that can be
Mm.
applied at the generation system reliability level,
Mm.
HL1 level,
Yes.
or value-based reliability for
Yeah.
capacity investment, or this could also be at the bulk system or at
Mm-hmm.
the distribution system
Yes.
level.
Okay.
So I think you are concerned more at the distribution system level
Mm.
with renewable energy.
Ah. Okay.
Uh, so in most of our students, they're developing their own software tool, and
Mm. Mm.
most of them have used MATLAB tools or
Ah. Okay.
uh,
Oh.
to do this in conjunction with other different students have
Mm.
developed different tools and they kind of combine this
Mm.
uh, but yeah but uh,
Mm.
I think here the challenge is uh, with renewable energy, when you calculate the expected energy not supply, not served, some researchers just use wind energy or solar energy as a negative load, and that really makes it very easy to do the calculation. Uh, you just come up with a modified load, but in cases where you have very high penetration of renewable energy, uh, all the energy cannot be absorbed by the system due to curtailment uh, of the congestion. And so therefore the right approach, in my opinion, is to consider them as generation sources and not as a negative load. So, and then also take into account the congestion in the lines, uh, so that uh, that the ENF that is calculated is more accurate in that sense. But this equation, this E cost calculation, IEAR multiplied by ENS, this is a very approximate method, because everything is lumped into the IEAR index.
Okay.
So but the assumption is that the IEAR index is quite robust, and it really doesn't change too much with the different scenarios. But again, this is an approximation. So the more accurate approach would be to actually simulate the frequency and the durations, and get a probability distribution of the different durations, and then use the customer damage function to find the cost for each of those durations.
Okay, thank you so much.
Yeah.
Okay, you have tried the MCS Monte Carlo simulator, is it right? Okay. Now.
Yes.
Okay. Yeah. Thank you so much. And so I am surprised that the HL1 as well as the HL2 level is the simulator you have simulated. It's very complex. Yeah.
Yes.
Now
Yes.
Yeah. Thank you. Yeah. Congratulations. Okay.
Yeah, thank you.
This is some Prof. Karki, before closing your speech, and so can I introduce Mr. O, Ungjin O. Thank you so much for your permission. He's visiting the Univ Saskatchewan in the September or October. Is it now? Okay? Your office
It's closed.
Closed. Yeah, thank you so much, and I hope his joining is the Univ Saskatchewan your lab and since the September. Okay. Yeah.
Yes, we are very anxiously waiting for this to open, and so that we can welcome you in our lab. But as of now, it looks like it might go even beyond September. It all depends when the travel restrictions will be lifted.
Okay.
And once that is lifted, then I think we can proceed.
Hongjae, can I want to some comment about he's visiting Univ Saskatchewan, okay, in Canada. In winter is the Saskatchewan is the minus 40 degrees Celsius. Is it right?
Yes. That is when we have our peak demand.
Yeah. Okay. comment 할래? 잠깐 할 수 있나? 간단하게.
Good to see you, Professor Rajesh Karki. And thank you for your interesting presentation. I will try to understand your presentation. And it's an honor to visit your university. So thank you for your assets to visit Saskatchewan. So I hope I will meet you as soon as possible.
Okay, looking forward to it. Thank you.
Okay, thank you so much for your first Karki, and thank you so much for your time. Okay, please, my best regard to Roy Billington. Okay.
I will do that. Thank you.